In this example, they're asking you to determine all global extrema. So that means absolute maxes and absolute mins, or global maxes and global mins, of the given function on this specific x interval. So they'll use the term global extrema. They can use the term absolute extrema. We're really looking for the absolute max and the absolute min, the largest and the smallest y value inside our given interval. The process for doing this is very similar to a first derivative test. It's just a slight bit easier in my opinion. So step one is going to look just like step one of the first derivative test. You need to find your first derivative. So we take our given equation, f of x equals 3x to the fifth minus 20x to the third, and we need to find the derivative of that equation. Well, that's just a bunch of stuff being added and subtracted. So to find our derivative, we're just going to follow our power rule. We're going to bring the 5 down. That gives 3 times 5 gets us 15x. Subtract 1 from the power gets us x to the fourth. Bring the 3 down. 3 times negative 20 is negative 60x. Subtract 1 from the power gets us x squared. So step one of our process is complete. On to step two. Step two of the process is the same as a first derivative test. We need to find our critical values. So remember that when you go to find critical values, you find critical values in two places. You find critical values when your derivative equals 0. That's the one most people remember, but you will also find derivatives whenever, or critical values whenever your derivative is undefined. The most common places to look out for it being undefined is if you have a fraction going on and you have x's in the bottom of your fraction and you need to worry about where you would get division by 0. The other one that's more important to us on this problem is also at the endpoints of your interval. The derivative is not defined at those endpoints, so those will be critical values as well. We're going to start off, we'll deal with the one that everyone knows. That's taking our derivative here and setting it equal to 0. So we get 0 equals 15x to the fourth minus 60x squared. To do the algebra on this, really anytime you've got a power of 2 or greater in your problem, the method is almost always going to require you to factor. And so that's what we're going to do here. We're going to start by factoring out whatever we can from both of these pieces. So looking at the numbers first, I can pull a 15 out of both pieces. And then looking at my x's, I can pull an x squared out of both pieces. What that'll leave me, I pull the 15 out. I pulled 2 x's out, so that's going to leave me 2 inside. I get minus, pulling 15 out of 60 gets me 4, and then I pulled all those x squareds to the front. The reason that we do this is now that these things are being multiplied, we can really break these up into two smaller bite-sized math problems. So we want to know whenever 15x squared equals 0, that'll be our critical values, or whenever x squared minus 4 equals 0, that'll also give us critical values. So working on that 15x squared one to start with, you would just go ahead, divide both sides by 15. We're just trying to get that x by itself. And then x squared equals 0, you would just square root both sides of that, and you would end up with x equals 0. When you're working on a global extrema problem that has a closed interval, really any problem you're dealing with that has a closed interval, you always need to check that these critical values are inside that interval. If they're not, you throw them away and you do not use them in the rest of your process. 0 here does live between negative 1 and 3, so that's going to be good. So that is one of our critical values. Now we're just going to keep doing the same process over here with our x squared minus 4. Solving for x, we'll add 4, add 4. We end up with x squared equals 4. And then we're just going to, again, cancel out that squared by square rooting both sides. And out of here, because we did the square rooting, that means we get a plus or minus the answer. So we will get plus or minus 2. That really is giving us two potential critical values. We've got one at x equals negative 2, and then we have another possible critical value at x equals 2. We again check them against the interval that we're given. So negative 2 does not live between negative 1 and 3, so we throw that away. That is bad, and we don't want to use it any longer. Then looking at 2, 2 does live between -1 and 3, our interval, and so that is going to be one of our critical values. The last piece to consider is that undefined situation for critical values. And when we have endpoints, those are going to be critical values for us. We have endpoints here. We've got a closed interval, so we're going to have both of those endpoints, x equals -1 and x equals 3. Those are also going to be critical values for us. Once you've done step 1 and step 2, again, same as you would do during a normal first derivative test, we go on to step 3. Step 3 is where things change in our process. So step 3 here is we just need to find the y values. These critical values we have, these are all the potential landing spots for our absolute maxes and our absolute mins. So now we just need to see the y values that go with them. So we are going to plug them back into our original equation now, because the y values that we care about are the y values from that original graph. So we're going to do f of 0, that first critical value we found. We're going to do f of 2, the second critical value we found, and then we're going to do our two endpoint critical values, so f of -1 and f of 3. We're going to plug those x values into our equation to get the y values that go with them. And then from that list, we just choose the winner of the absolute max award and the winner of the absolute min award. So plugging 0 into that equation, we would get out 0. Plugging 2 into this equation over here, again, do this in your calculator, do it by hand, however you want to do it, you would get -64. Plugging in -1 to that equation, you would get out 17. And then plugging 3 into that equation, you would get out 189. Now that you have those, now it's really time to go ahead and just draw your final conclusions, give your answers. So based upon that list, the winner of the absolute max award would be this 189. And so you would say you have an absolute max of 189, the y value at x equals 3. The x value. So remember, the y value is always what that max or min is. The x value is when it occurs. Then on this one, our absolute min, the smallest y value, would be at 2 right there, at -64. So we would say we have an absolute min of -64 at x equals 2. It is possible to have two y values that equal the same thing. And it's okay. It doesn't say your absolute max only occurs at one place. It just says where is the largest y, what is the largest y value, and then where does it happen. If it happens in multiple places, you just add on to your list of where that absolute max or absolute min is happening. So global maxes, global mins, global extrema, absolute maxes, absolute mins, absolute extrema. This is your process every single time, very similar to the first derivative test. The only thing that changes is really step 3, where we plug everything back into the original function to get those y values and find out our final answer. Thanks for watching my video. If you liked it, please click that like button and subscribe. And also share it with your friends and anyone else you know who might be crying about an upcoming AP Calc test. You can find more videos from me, more sample AP Calc questions, and my complete AP Calc study guide over at my website, apcalcprep.com. Have a great one.